So far, I've talked about STN, which stands for Simple Task Networks. The more general approach is known as Hierarchical Task Network Planning, and that's what we will be looking at next. HTN planning is more general than STN planning, but that also means there isn't a single algorithm that implements HTN planning, so I can't show you any pseudocode here. Instead, I will just give you an overview of the general approach. In STN planning, as I have just described it, there were two types of constraints that were part of the representation and the procedure. The first type of constraint we've seen are the ordering constraints. And if you remember the definition of a task network consisting of nodes and edges, these edges represented the ordering constraints. So they were built into the representation of a task network. This means there was exactly one way in which ordering constraints between tasks could be handled. The other type of constraints we've seen are the preconditions. Preconditions are constraints on the state before a method or an action is applied. And what we've done in HTN planning is that we've written it into our planning procedure that preconditions must hold. So preconditions were enforced by the procedure. And to be able to enforce preconditions, the planning procedure had to rely on knowledge of the state before a method or an action was applied. So we must know what exactly that state is to be able to test for applicability. And that means we must perform forward search because of the way we've represented preconditions as part of methods in our approach. In HTN planning, we try to take a more general approach. HTN planning does not deal with a specific type of ordering constraints or a specific representation for preconditions, but maintains general constraints explicitly as part of the representation. So of course, this will require additional bookkeeping, but it means we are much more flexible. If we want to have a different type for ordering our network, then we can plug a different constraint management system into our HTN planner. Similarly, for other types of constraints we want to handle, they can be included in our representation as part of a general constraint network having different types of constraints. Although I won't go into as much detail as before, I at least wanted to give you a flavor what HTN methods look like by presenting you with a formal definition here. This will allow you to at least contrast STN and HTN methods. So we start off with a set of method symbols that we use to uniquely name our methods, just as for STN planning. Then we say an HTN method is a for-tuple consisting of four things, and these four things are: firstly, there is the name of the method, and that name is, just like for STN method, consisting of a method symbol, and then has a syntactic expression of the form n of x1 through xk, where n is a method symbol, n is an element of our set ms, and x1 through xk are the variables representing the objects that are manipulated by this method. So this is exactly as for STN methods. And then also, like for STN methods, is the task of the method, the second component. This must be a non-primitive task that is accomplished by this method. And then again, as for STN methods, we have a set of subtasks. These are the tasks into which the method breaks down. So far, there's nothing new. What's really new is that we have a set of constraints associated with an HTN method. And we're not going to be specific here about what types of constraints these are. These can be simple ordering constraints of the type we've seen them, or they can be precondition constraints of the type that we've also had in STN methods, or they could be more complex things, like we could have time point networks if we want to do more elaborate temporal planning, or we could have constraints on the resources that are consumed by the different tasks in our method. The HTN approach is not specific as to which constraints necessarily must be involved here. So let's look at an example of an HTN method, and again we'll use an example from our DocWorker robot domain, the example we've seen previously as an STN method. We want to move the topmost container from one pile to another, and this is again a take action followed by a put action. So As I've said before, the first three parts are actually the same as before. So we have a method name describing this method, then we have a task that is accomplished by this method, and the method name contains the same variables representing the same objects as before. Also, the task is the same as before, so I won't go into this in detail. What is new is the network of subtasks here, consisting of subtasks as before. But what I've also done is I've given these subtask names that allow me to refer to them in the constraints. So the first subtask is called T1 here. That's a local name for the subtask. And the second one is called T2. Other than that, the subtasks are the same. But then I add general constraints to this network to complete this HTN method. And the first constraint I have is that T1 must be before T2. So that's an ordering constraint I add here. Then I have other constraints representing the preconditions. Looking at this example, I'm saying here that before the set T1, so this is a set of tasks, there could be more than one here, we must have the condition that the container C is on top of the origin pile true. So that's a before constraint applied to a set of tasks and a condition. And we have several other constraints of this type here that effectively represent the preconditions of the HTN method as we've seen it previously. But one thing that is different here is if you look at this constraint here, here we don't have a T1 but a T2, and we have the same here for the second precondition. What this is saying is that these two conditions must only be true before the second task in the network. So we can be more specific here about where we want preconditions to be true. And looking at the second one, we only need the fact that XD, the destination container onto which we're putting our container, needs to be at the top of the destination pile before we put it down there. And when you think about it, that makes a lot of sense. There's no need for this to be the case before task 1, but instead, before we put down the container, we must have this true. So this approach of handling constraints like this can be more explicit as to where those constraints must be true. But sometimes a more general approach can also come with difficulties, and that's what the second example of HTN methods illustrates. This is again taken from our DocWorker robot domain, and it's the example of moving a stack by repeatedly moving the topmost container until the stack is empty. And again, we have two methods that accomplish this, and these are the recursive move method we've seen earlier, from PO to PD, moving container C from container XO, and it accomplishes the task of moving the stack from PO to PD, and it has the following network of subtasks. The tasks themselves haven't changed, so again we have moving the topmost container and then moving the stack. We've introduced names for those tasks so that we can refer to them in the constraints. The first constraint is the ordering constraint, and the preconditions are attached to the first task. So there's nothing different about this first HTN method from the STN version we have seen earlier. But the second method shown here, move1, is very different from no move, what we've seen earlier in the STN methods. And the reason for this is that constraints are always attached to the tasks in our network. So if our network consists of no tasks, then we really can't attach any constraints to this method. And that is of course what we had in the no move method. There were no tasks, so in this approach we couldn't attach any constraints. What we've got to do to solve this problem is simply introduce a method that moves the last container in the network, and that means we only have one subtask moving the topmost container, which is the last here, and we add constraints to this subtask that ensure that this is actually the last container. So it needs to be on top of the pile, but more importantly, the container that we are trying to move here must be on the pallet, and if it's on the pallet, it's the last container in the stack. So you can see it's not all that different from an STN method. I want to take a step back now and compare HTN planning to the strips planning we've seen previously. And the first thing I want you to understand is that HTN planning is far more expressive than strips planning. So you can encode problems in HTN that you can't encode in strips planning. And this applies to HTN and STN planning alike. So I will argue here that this holds for STN planning. And since HTN planning is a generalization of STN planning, it will also hold for HTN planning. And the way you can see that STN planning must be a more powerful approach is by seeing that STN problems can be undecidable. So thinking back to strips planning, what we did was we encoded a finite search space. We had a finite number of objects, a finite number of predicates, which means we have a finite number of combinations, how we can build up world states, and we can do a graph search in the state. So it cannot possibly be undecidable whether there is a plan or there isn't a plan. Strips planning may be hard, but it is decidable. To see that STN planning is undecidable requires a little more background. But when you compare the STN formalism to programming languages, you will see that they are quite similar. In fact, the basic constructs you find in any programming language are also in STN planning. You have branching by having alternative methods that have different preconditions. Just think back to the second example we've just seen. And we also have methods that accomplish a given task, but have the same type of task as a subtask. So these methods are effectively recursive. And with recursion and branching, we have the power of a general programming language. And that is why STN planning is so powerful. The STN, and therefore the HTN formalism, is more expressive than strips planning. That's what you need to remember here. But if you leave out the recursive aspect from STN planning, so if you have no methods that are effectively recursive, then you can translate these domains into equivalent strips problems that solve the same problem. Unfortunately, this translation process may lead to an exponential blow-up in the size of the problem. As a final point, there is also a set of STN domains called regular STN domains, and that also is equivalent to strips planning. Regular STN domains contain some degree of recursiveness, but not much. So this is the end of this segment about STN or HTN planning. I've told you all about tasks and task networks, which were the new nodes in our search space. We've seen what methods are. They refine task networks to give us state transitions in our search space, and the way they do that is through decomposition of tasks in the networks. Then we've seen the usual definitions of problems and solutions, and we have seen how we can do planning with the TFD and PFD algorithms. This whole approach can be generalized to HTN planning, where we explicitly handle constraints of unknown types. And although I've just compared HTN and strips planning, keep in mind that these two approaches really solve two different types of problem. The one is goal-based planning and the other is task-based planning. And that concludes this segment.